And here it is, and it's called subspace inconsistency. So what is the idea here? Well, first of all, it works best for categorical data, as you just will find out here. So given a data set, if we have categorical data, then we will probably have a lot of identical vectors, having the exact identical values in the categories, in the different features. Yeah. So when looking at identical vectors in a particular subspace or in a particular feature space, they should have the same class label, right? If they don't have the same class label, it's a kind of inconsistency, yeah, because two identical vectors should have the same label. Otherwise, it's inconsistent. So if we can somehow measure how many vectors do not agree on their class labels, then we can measure the inconsistency in the particular feature space. And that's exactly the point, what this subspace inconsistency measure tries to evaluate, actually tries to explore. So we measure two things, count simply two things: the amount of all identical vectors of a given instance of the data set. Yeah, so for example, if you have, I don't know, if you have two dimensions, then all vectors that have the same values in these two dimensions will be one instance of this U here. Yeah, so XRU is the amount of all identical vectors of a given instance U in a given feature space R. And we also are interested, of course, in all the vectors, identical vectors, that have the same class labels. And that is the one that is denoted here. So this is here, this term here is the amount of all identical vectors U as before, but now only those that have the same class label. Yeah, and obviously in the best case, this number here equals this number here. Yeah, in the worst case, we have many different things. So for example, if we have two classes, we have a 50-50 partitioning. So we have so this one here is just 50% of this one here. Yeah, so that would be somehow the worst case. So the inconsistency of a given instance, of a given combination of features of the feature space R, especially if it's categorical, can be then just computed by taking all identical values of U, which is this one here, minus the maximum of all identical values that have the same class labels. Yeah? Since we have multiple classes, typically we just take the maximum of those different measures here. Because in the best case, once again, this is exactly the same number as this one here. So in the best case, the whole thing is 0, obviously. Yeah. So inconsistency of U, of a special value combination U, would be 0 in the best case. In the worst case, it's somehow 50% or something, or C% of the whole thing, or 1 divided by C. Yeah. So and now, since we're just looking here at one particular instance, one particular value combination U, we have to do that over all possible value combinations that actually appear in our feature space. So that's what it's done here. So we look at all possible, not all possible, but all appearing value combinations U in our data set, and calculate this inconsistency of this value combination U. Yeah? And that is then normalized by the number of instances in the whole thing. Yeah? And well, of course, we see that the smaller the better. So we want to minimize this inconsistency value, and this value is actually monotonic. Why? Well, it's just stated here because if we have a projection of R2, which is R1 here, R1 is the lower dimensional projection of R2. Yeah, that is this subset relationship. Then the inconsistency value of R1, sorry, is greater or equal than than that of R2. So the inconsistency gets worse. It gets higher, since we are interested in minimizing that. An increase means the whole thing gets worse. Yeah, so the quality actually decreases. Yeah, and that's actually what we need for monotonic branch and bound. So we can apply that here easily. And why is that the case, actually? So I just asked, why is that the case? I just said that this is the case, but why is that the case? Well, if you consider, R2, in R2 we have more features, in R1 we have less features, yeah. And obviously, if you have a look at these numbers here, if we delete a feature, then the same values that had the identical values in the remaining features, yeah, are still in this number here. Maybe the number here increases, but this number here will decrease, actually, yeah. So in that case, the whole thing just increases, yeah, obviously. So if we think about it a little bit closer, it makes sense, obviously, yeah. So if we delete a feature, we can only get more inconsistent than consistent, obviously, yeah, because less features mean that of course we have a less discriminant feature space, so the consistency with the class labels can only decrease, yeah. So the inconsistency will increase. That's, I think, quite intuitive also, yeah, but think about it again. Yeah, so backward elimination with branch and bound. So if the monotonicity applies, then we can use that to kind of efficiently search for the optimal solution. So in the branch and bound algorithm, we get the optimal solution. And that is especially well suited for binary or discrete data, because then, especially this subspace inconsistency measure, because then we have these identical values or vectors, value combinations, and they are not only very likely, or these identical vectors are very likely with decreasing dimensionality. So the number of identical values increase with decreasing dimensionality, and also the inconsistency obviously increases in that case. Yeah, limitations: it's useless without groups of identical features. Yeah, for example, if you have real valued vectors, what is a value combination U with identical vectors? They should have a consistent labeling, yeah, but we could employ, of course, some kind of similarity threshold, but what is the threshold and stuff like that? So if we have real valued vectors, the whole thing is a little bit less sensible, less meaningful, yeah, and up to useless, actually. Yeah, and I mean, this branch and bound thing here, this looks pretty, or sounds pretty good, yeah, pretty efficient, but still the worst case complexity is the complexity of the search space, which is still 2 to the power of d, in that case 2 to the power of 4. So we have 2 to the power of 4 many possible branches or nodes in this search tree here. This is a kind of search tree, yeah. All the nodes are candidates that need to be either refined further, like those here, or are candidates at the end in the target dimensionality. Yeah? So in the target dimensionality, of course, we only have 4 candidates in that case, so it would be probably a little bit better to just compute the target dimensionality candidates and then do that. But that's a little bit a Mickey Mouse example here. Typically, the number of candidates in the target dimension is much higher. Yeah? So in that case, we can apply that, but still the entire search space is the worst case complexity for that. So that is meant with worst case runtime complexity is still exponential in the number of features. So still 2 to the power of d, and that is, of course, not a nice thing in that sense. No? Okay. Yeah, and as said before, here in that subspace is somehow a kind of Irrläufer, yeah, shouldn't be here. So random subspace selection will be next here on the next in the next subject. Just that you already know, the general approach is that you select randomly some subspaces having the target dimensionality. Yeah, so how many are there if you have n dimensions in the original feature space? Sorry for inconsistent use of n and d in that case. So if you have n original features and we want to keep k, we have n over k many possible subspaces, and if n is large and k is large, or not so, well, if n is large especially, but also k is large, then it's quite a bit. So we don't want to evaluate all of them, but just randomly select subspaces out of these n over k, many. Yeah. And that of course needs a quality measure of again for complete subspaces, and of course there's a trade-off between quality and effort depending on how many sampled candidates I'm looking at. Yeah. And but still it's a good alternative to forward selection if the quality measure is not monotonic actually. Yeah? So and we'll have a look at different randomization approaches, genetic algorithms, k-mediated feature clustering. There are many more, but we will have a look at these two in the next subsection, meaning in the next podcast.